Now question number 1 is, for any polynomial pt, the limit t tends to infinite pt upon e to the power t is independent of polynomial p. Justify the statement and find the value of this limit. So we have this limit which is limit t tends to infinite p as a function of t upon e to the power t. Now if we put t as infinite, this numerator will be plus or minus infinite, and then e to the power infinite will be infinite. So when it is infinity upon infinity form, we can use L'Hopital's rule. And if we use L'Hopital's rule, we can write this as limit t tends to infinite p dash t upon e to the power t. Then again it will be plus minus infinity upon infinity. So we can differentiate it again. We can keep using L'Hopital's rule till we differentiate this function n times, which is degree of this polynomial. And if we differentiate this polynomial up to its degree, then it will be some constant upon infinite, and any constant upon infinite is simply 0. So this statement is true and the value of this limit is simply 0. So that's your part A. Now part B is, show that q dash 0 exists and find its value. And why is it enough to calculate the relevant limit from only one side? Now we'll find q dash 0 positive. Now q dash 0 positive will be limit h tends to 0 q 0 plus h minus q0 upon h. Now this is limit h tends to 0. Now q h positive when x is greater than 0 is simply e to the power minus 1 by h. q0 is 0 and here it will be this h. So we can write this as limit h tends to 0 1 by h and then e to the power 1 by h. Now what we will do is we'll let 1 by h as t, then we can write this as limit t tends to infinite t upon e to the power t, which is of the form pt upon e to the power t, and we know that this limit is equal to 0. So q dash 0 positive is 0. Now we need not calculate q dash 0 negative, as this given function is an even function. So suppose we have to find the value of q minus 2 will be e to the power minus 1 by 2, and which is same as value at 2. So this given function is an even function. So we just have to calculate limit from only one side. So this q dash 0 exists and its value is simply 0. Now part C is, for any positive integer n, show that qn0 exists and find its value. Here qx is the function in part B and qn0 denote the nth derivative at x equals 0. Now what we'll do is, for this part C, we have to find nth derivative of this function at 0. Now we know that qx, it is an even function. Now if qx is even, q1x is odd, q2x is even, and continues. So we can say this q&x will be even when n is even, and will be an odd function when n is an odd function. So we can simply write qn minus x will be minus 1 to the power n q nx. Now if we look at this function, which is qx, when x is greater than 0, it is e to the power minus 1 by x. Now q1x will be e to the power minus 1 by x into 1 upon x square. Now we find q2x will be e to the power minus 1 by x minus 2 upon x cube plus 1 upon x square e to the power minus 1 by x, and then 1 by x square, which is e to the power minus 1 by x minus 2 upon x cube plus 1 upon x to the power 4. Now we keep differentiating it. We can write Q(n)x LB of the form e to the power minus 1 by x and then some polynomial expression of 1 by x. Now if we have to find Qn0 positive, it will be this limit h tends to 0 e to the power minus 1 by h p 1 by h. If we let 1 upon h as t, we can write this as limit t tends to infinite pt upon e to the power t, and this we have already established in part A that this is equal to 0. So from here we can say this Qn0 positive will be equal to Qn0 negative and it will be equal to 0. That is, this Qn0 will exist and it is equal to 0. Now in question number 2 we are given that let p, q, r be real numbers such that p square plus q square plus r square equals 1. Then we are given this expression. We have to prove that it is less than 2 and we have to find its smallest and largest value. So let this be y. So this is 3p square q plus 3p square r plus 2q cube plus 2r cube. Now what we'll do is we'll add q cube and r cube and we'll subtract q cube and r cube. So here we'll take them together. We can write 3q p square plus q square, and here we'll take 3r common, will be p square plus r square minus q cube minus r cube. Now p square plus q square is 1 minus r square. So we can write this as 3q 1 minus r square, and here will be 3r 1 minus q square and minus q cube minus r cube. So it will be 3 q plus r and then minus this q plus r whole cube. Now what we'll do is we'll let q plus r as sum x, then this y will be 3x minus x cube. Now here we need to find range of x also. Now we know that q minus r square is greater than or equal to 0. We can write q square plus r square, it is greater than or equal to 2qr, and if we add q square plus r square, we can write 2 times q square plus r square, it will be greater than or equal to q plus r whole square. Now q plus r is nothing but x. So from here we can write x square will be less than or equal to 2 q square plus r square. Now q square plus r square is 1 minus p square. That is, it is always less than or equal to 1. So this is always less than or equal to 2. So from here we can write x square is always less than or equal to 2. That is, value of x should lie between minus root 2n plus root 2. Now we have to find absolute maximum and minimum of this function in this interval. Now what we'll do is we'll find dy by dx. dy by dx will be 3 minus 3x square. That is, the value of x will be plus or minus 1. Now if we find the value of y at 1, it will be 3 minus 1, which is 2. Value of y at minus 1 will be minus 3 plus 1, which is minus 2. Value at root 2 will be 3 root 2 minus 2 root 2, which is root 2, and value of y at minus root 2 will be minus 3 root 2 and plus 2 root 2, which is minus root 2. Now are these 4 values? This is absolute maximum and this is the absolute minimum. So from here we can say this y, it will always lie between minus 2 and plus 2, and which also proves our first part, that is this expression is less than 2. Now we have to specify exactly when the smallest and largest possible value is achieved. So we are going to achieve this smallest and largest value when the value of x is plus or minus 1. If we put x is plus or minus 1, we'll get this condition that the value of q plus r should be plus 1 or minus 1. Now question number 3 is, show that there are exactly two numbers a in 2, 3 up to 9999 for which a square minus a is divisible by 10,000. Now we know that this 10,000 is 2 to the power 4 into 5 to the power 4. And we can write this a square minus a as a into a minus 1. Now we know that GCD of a into a minus 1 is 1. That is, a and a minus 1 are relatively co-prime. So we have two cases. Case 1, when 2 to the power 4 divides a and 5 to the power 4 divides a minus 1. And the second case, when 5 to the power 4 divides a and 2 to the power 4 divides a minus 1. Now we can write this as a equals sum 2 to the power 4 into k1 and a minus 1 will be 5 to the power 4 k2. So we compare it, we can write 16 k1 will be equal to 625 k2 plus 1. Now we can write 625 as 16 into 39 plus 1 k2 plus 1, and this is 16 k1. Now this LHS is congruent 0 modulo 16, and this RHS is congruent to k2 plus 1 modulo 16. That simply means that the value of k2, it must be 15. And if we put k2 as 15, then the value of a will be 1 plus 625 into 15, which is 9376. And for the second case, we can write this a as 625 k1 and a minus 1 as 16 k2. We can write 625 k1 equals 16 k2 plus 1. Now again, if we take modulo 16, we can write left hand side is k1 modulo 16 and right hand side is a 1 modulo 16. That means the value of k1 should be 1. And if we put k1 as 1, value of a will be 625. So there are two values of a which are possible. One of them is 9376 and the other one is 625. And the second part, it says, let n be a positive integer. Then for how many numbers a in 2, 3 up to n square minus 1, a square minus a divisible by n square. Now, if this n is a prime number, say n equals some p, then if p square divides a minus 1, in that case, 1 of a or a minus 1, it is equal to 1, which is not possible. So if n is a prime number, then in that case, no value of a is possible. Now we get the same scenario if n is not prime, but it is some power of prime. Suppose p to the power e. In that case also, if p to the power e divides a into a minus 1, then either a is 1 or 2, which again is not possible. So this n, it cannot be a prime number or some power of single prime. So this n, it must be a composite number. So if n is a composite number, then we can write n square as some prime p1 to the power e1, prime p2 to the power e2, and then some pk to the power ek. Now this n square, it divides a into a minus 1. And since a and a minus 1, they are co-prime, that means some of the prime factors, they'll be in a, and other prime factors, they'll be in a minus 1. So basically, we have to find number of prime factorization of n square. Now, for number of prime factorization of n square, for each prime, we have two choices. Either it'll go to a or a minus 1. So, for P1, it'll be two choices. For P2, it'll be two choices. And then for Pk, it'll be two choices. So, total number of cases will be 2 to the power k. And from this, we'll subtract two cases when the factorization is of the form 1 into n square. In that case, either a is 1 or a minus 1 is 1, which is not possible. So, total number of ways in which we can find prime factorization of n square is 2 to the power k minus 2. Now, this n square is a composite number, say x into y. Then, Chinese remainder theorem, it tells us that we can always find this a, which is 0 modulo x and which is 1 modulo y. And this modulo will be unique because if there are two solutions, then the difference will also be divisible by xy, which is not possible. Each case, there will be one value of a possible. So, answer to this question is, if n is prime, then there is no such a possible. If n square is of the form p1 to the power e1, p2 to the power e2, pk to the power ek, then the number of values of a possible is 2 to the power k minus 2. Now, question number 4 is, the function f is defined on R to R and let it be a twice differentiable function such that f dash x minus f dash y will be less than or equal to 3 times mod of x minus y. Now, if we interchange x and y, we can write this as f dash y minus f dash x will be less than or equal to 3 times mod of x minus y. That is, from here we can clearly say that this mod of f dash x minus f dash y, it is less than or equal to 3 times mod of x minus y. Now, what we'll do is, without loss of generality, we'll assume that x is greater than or equal to y, and when we fix x and y, we'll define this t as some x minus y, and this t will be greater than or equal to 0. Now, if we choose some h which lies between 0 and t, if we take this x as y plus h, we can write this as mod of f dash y plus h minus f dash y will be less than or equal to 3 times mod h. Now, what we'll do is we'll integrate both sides from 0 to t. Now, we know that integral of 0 to t mod fx dx, it is greater than or equal to mod of this integral fx dx. So, we'll write this mod of integral from 0 to t f dash y plus h minus f dash y dh, it is less than or equal to from 0 to t 3 mod h dh. Now, if we integrate this function, we'll get this as f y plus h from 0 to t minus f dash y into h from 0 to t, it is less than or equal to 3, and this is h square by 2 from 0 to t, and it'll be mod f y plus t minus fy minus f dash y into t will be less than or equal to 1.5 t square. Now, t is x minus y. If we put x minus y, it will be mod of fx minus fy minus f dash y into x minus y will be less than or equal to 1.5 x minus y square, and this is what we need to prove. Mod of fx minus fy into f dash y x minus y, it is less than or equal to 1.5 x minus y square. Now, B part is find the largest and smallest possible value of f double dash x under the given condition. So, for that, we'll use this condition, which is mod of f dash x minus f dash y, it is less than or equal to 3 mod of x minus y. Now we can also write this as mod of f dash x minus f dash y upon x minus y, it is less than or equal to 3. Now we'll take this limit y tends to x. Now we take limit y tends to x, then on the left hand side this expression is nothing but f double dash x. So we can write this as mod of f double dash x will be less than or equal to 3. Now when mod x is less than a, x lies between minus a and plus a. So we can write f double dash x, it will lie between minus 3 and plus 3. So its smallest value is minus 3 and its largest value is plus 3. Now question number 5 is, for an arbitrary integer n, let Gn be GCD of 2n plus 9 and 6n square plus 11n minus 2. Now if we divide 6n square plus 11n plus 2 with 2n plus 9, we can write this as 2n plus 9 and it will be 6n square plus 11n minus 2. So this is 3n, 6n square plus 27n and then minus 16n minus 2. So it will be minus 8, it will be minus 16n minus 72. So plus and minus. Now we can write this 6n square plus 11n minus 2 as 2n plus 9 comma 2n plus 9 into 3n minus 8 plus 70. So GCD of 2n plus 9, 6n square plus 11n minus 2 will be equal to GCD of 2n plus 9 and 70. Now this GCD is Gn. That means Gn divides 70 and Gn divides 2n plus 9. Now if Gn divides 70, then Gn can be plus minus 1, plus minus 2, plus minus 5, plus minus 7, plus minus 10, plus minus 35 and plus minus 70. But Gn also divides 2n plus 9. That means this Gn, it must be an odd number. So Gn now cannot take even values. It can take only odd values. So the largest possible value of Gn is 35. So the largest positive integer that can be obtained as the value of Gn is simply 35. And we'll get this value as 35 when 2n plus 9 is 35. So 2n is 35 minus 9, 26. When the value of n is simply 13. Now in question number 6, we are given a circle, one of its diameter AB and a point X. Now first part is, using only a straight edge, we have to show that how to draw a line perpendicular to AB and passing through X. Now we complete this triangle AXB. Then we know that this is 90 because this is angle in a semicircle, and the same way this angle is also 90 degrees. So this point, it is orthocenter of this triangle ABX, and if we join H with X, this is the perpendicular that we need. So that's your part A. Now part B is, do not draw any of your work for this part. Reconsider your procedure to see if it can be made to work if the point X is in some other position. Now first case is, if this X, it lies on this line AB. So if X lies on AB, we cannot draw perpendicular from X to AB. Second case is when X lies on a circle. If X lies on a circle, then this triangle ABX it'll be 90 degrees. And since we do not have any other altitudes, then also we cannot find perpendicular from X to AB. So in this case, our first method, it is not going to work. And then this third case, when X lies on any of the tangent passing through two extremities. So if X lies on either tangent through A or tangent through B, then if we follow that method, when we'll join X with A and X with B, so with B, we'll have this point, say D, but there won't be any C. In that case, this is a perpendicular itself. So these are the cases possible for different positions of X.